to start. So last time we did some numerical solution of ordinary differential equations, where we first started with the Euler method of solving them, and then the improved Euler or modified Euler, which has a small correction term, this, which is called Heinz method. And then we went over to Midpoint Method and Runge-Kutta method. And we stopped at 2 method. So I'm just going to briefly show them again. Blackboard. Oh. So this is loading. Let's see if we... Okay. So this is a slightly different... Oh. Then you should be able to see what I'm seeing. There we go. Okay. There's a slightly different function than what we had last time, but the idea is here just to see there's an error. You see, this is one of the ODEs we are actually able to solve analytically, and the analytical solution is black line. Numerical Euler, we undershoot. If we try to correct this undershooting, last time we just had a better estimate, but it could also be that we overcorrect. You see that the Heinz method, it is closer. The absolute value of the error is less. Look here, it's almost 40 at the end, and this is 15 or something error. It's better, but it's overshooting. Next, midpoint method. In this case, fairly decent estimate. And next, or method. Fairly deep. And the Rk4 method is a very popular method, and it's often used, or a modification of. So first I present the fourth order Runge-Kutta method, and then some improvements to it. What can we improve here? Well, if we do some calculation with the error, maybe we could have a longer step length or a shorter step length, an adaptive step length. Predictor-Corrector Method. Cool. So, fourth order Runge-Kutta. This is going to be a lot of equations on the blackboard. You don't need to write them all down. There will be 13 equations. So this is the most used. I'll get back to why it's the most used. That's because you have best error as a function. No, yeah, the best error as a function of function evaluation. We'll try to list them all later. The most uses Rk method. If you've used the function ODE45 in MATLAB, it's based on the Runge-Kutta. So for 5, it's not 45, based on the Runge-Kutta 4 and 5 methods. It also gives a good balance between accuracy and computation cost. additional cost. Okay, so if you remember, almost a week ago, we are comparing function evaluations to Taylor expansions. So in this case, we want to solve y I plus 1. Okay, so that's, we know this, we want to calculate this. This is a so-called explicit method, since you can actually solve explicitly for the next step. So in the next lecture or tomorrow, we will have about implicit methods. Omega 1, K1. So omega 1, a scaling of function evaluation K1. I will write what this omega 2 K2 plus 3 K3 plus fourth method or K4, where K1 function K Y so K or I, it's the same. It's just we have used I over there and I'm using K here. It doesn't really matter. Just a counter. First one, and then this omega is how much we want of that. K2 to be TK, some kind of variable 1, H. H is the step length. K, B1, K1. K1, this is this function, so we can actually read K3. We're using K2 in this, TK plus 2H, 1K plus B, K1 plus B, K2. We're using the two previous ones. K4, we'll use all the H, F, TK plus 3H, 1K, and might ask, where do I get all of these variables from? Well, people who have solved this before, they see that I need to introduce all of these variables. Be able to fit this to Taylor expansion. Four, 1, B5, K2, B3. And I will just skip the Taylor expansion that show you all of the 13 equations that needs to be solved in order to save this. Oh, with me. Well, the first one, B1 equals A1. Okay, that one's easy. If you know one of them, we know the other. We know that B2 plus B3 A2 and B4 plus B5 plus B6 So far so good. These are just linear equations. But next, omega 1 plus omega 2, 3 plus omega 4, 1, still only linear, then it becomes a bit more complicated. A1 and if you want, you can just take a picture of the blackboard writing all of this up. 3, this 1/2 omega A1 squared 2 squared 4 should third there again. A1 3 plus omega 3 A2 3 plus omega 4. Yeah, there's a it's a lot of equations, but it's good to have them one time. Okay, so that's that done with. Omega 3 A1 A1 B 3 plus 4 B1, and I know this is getting ridiculous. B5 plus 2 6 sixth. I could also mention that we have 13 unknowns, but only 11 equations. Describe them. 3, so what do we have to do then? I'll let you think. Four, 3, A1, 5, A2, B, 6, S1, 8th, and we have 2 more. Squared plus 4, A1 squared, 5, squared, B6, 12th, and last omega 4, B1, B6. Thank you for the patience. Okay. So, this is what you end up with. Do you want to do another one for Rk5 as well? I don't. I don't have them in my notes either. But as you can see, the problem here is 11 equations. So let's see if I get it correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if you have been counting, we have 13 variables. What we have to do then is pick 2 of them. That's sometimes how it is. I guess you've seen that when you've tried to do programming, you have to do a lot of just arbitrary guessing or picking. You just see if it works. So, some clever guys have seen that if you set a 1/2 2, 0, we get, these are the one we pick. Then we can solve of these. A2 is a half. A3, 1. So 2 is a half, A3 is 1. B1 is half. We have already picked B2. B3 should be half. And B4, 0. So how I imagine they've picked this is you look at the error and you want to minimize the error. That's how you pick these two at the bottom, at the top. B6, 1, and omega 1, 6th. Omega 2 is a third. 3 is also a third. Omega 4. Okay, so what do we get for numbers? So this is the most common Rk4 method. Picking those at the top, solving these 11 equations, and getting the rest of the 11 ones. So here, so this is the general form of them. Then we end up with y, k, 1 equals y, k, h, 6, 1, k, 2, okay, plus k, 3, 4. Yeah, because and then try to get it aligned. K1. Well, there's no variables there, so this is t y k 2 to be f of k plus h over 2 y k plus h over 2 k1 t k h over 2 y k plus 2. Okay, so we don't need k1, 3, b2, 0. So we save. K4, f tk plus h, y, 3. And basically just solve in a cascading manner. So placeholder variables. Okay, so the most important bit here is this. And again, you pick h. That's a step length. How can we actually pick the step length a good way? Well, again, looking at the error. To do the calculations for Rk4, we'll see that it is of the order looking at, so I've presented Rk2 and Rk4. Of course, you have Rk3 and 5 and 6 and 7 and 8. And you would think that if you increase the number of function evaluations, you would get a better error. And that is by and large true, only you don't get as much back from it. So, this computational cost versus error. Function equals or Rk number and best error. So if you pick some of these variables in a wrong way, you will get a higher error. But the best error you can get is what I'm going to write here now. So if you have the Rk2, best error you can get is h2 squared. That makes sense. Same goes for number 3. 3. Again, the number here is the amount of function evaluations you have to do each step. As you say Rk4, well, you have to solve the function 4 times. You can actually reuse some of the steps also. Big OH4. And what do you think the next one will be? 5? So for the ones between 5 and 7, 7 h to the power of n 1. What does this tell us? So if we have the Rk5, we have more function evaluations, one more function evaluation, but n minus 1, that's 4, so we get the same error. So there's no point in doing Rk5. It only adds more computational cost. But you can use it to check your error. So even though it is the same h power, you will get somewhat less of an error, generally speaking. Go to 8, 9, even worse, h minus 2, and for n, this, even bigger, a big OH3. I mean, of course, you could go up, but you don't really gain that much. It is better to just reduce the step length. And this is where so-called adaptive methods come in. For instance, Rk4, 5. In MATLAB, this is the function ODE or 5. Or you could try ODE 3 instead. and then you only do either Rk2 and Rk3 check. So the idea to use two methods to check if the solution is good enough. So you can see if they differ too much. So if ODE or Rk4 gives you a very different estimate than Rk5, then you need to do something with your step length. So if the sols differ by too much, so too much, that's a preset value. Then we just halve the step length, or at least decrease it. So the trick here, in order to save computational costs, is to reuse function evaluations. Cost. Okay. So take a look at this. See if it's any better than our method. Parentheses. I'll show it in the program right now. So you don't see this. Yeah. Yes, this is encoded. I'll show you how to use it. If my Mac wants to join again. Reuse the function evaluations, func evals. It's just short. The problem here is that when you actually change the step length, you have to compute many more function evaluations again, unless you do some smart stuff. What I'm going to do now, I'm going to this one, so here we use Rk4, and then I'll compare our Rk4 method ODE45. So this is the implementation of Rk4. See, I put it in the same as behind the backboard or in your notes. Just K1 is function evaluation, I, YR, and then these variables. Once see, the error looks okay. It's fairly low. I mean, the step length we have right here now is very long. Try to run both in MATLAB 1. This. So it's basically ODE45, built-in function handle. The starting values, Ti of 1, that's the first, well, that's 0 in this case, so that's the first. Then the I of end, last one. And A. Yes, the starting value of this function. You always need to. So that's, you look in notes as y0, value of the y0. Okay? So first, take a look at this function. So Rk4, it fits fairly okay, I would say. Then you see that this OD45, it starts with very small step lengths, because in this I haven't really defined any step length at all. It does everything automatically. So just, oh, I'm gonna try, and then it sees like, this is good enough. So I can just increase, actually double the step length here. Then it looks like it's doubling the step length somewhere around here also. But you see, it's much more computationally intensive than our implementation of the Rk4, because we only have a few points, because the step length of ours is there. Yes? So this is the analytic. Okay, so all the way up then. So we are trying to solve this equation over here, the same as last week. So so we want to solve this. This is the equation, and this is the analytical solution of the equation. So I've just implemented two ways here. You can either this one and this one, or this one. That could actually be documented better. But the thing is, we're solving an ordinary differential equation that we can also solve analytically. So we have something to compare it with, see if it's okay. So that's the black line. That's the analytical solution, the exact solution. And this is our estimates. So we can do this in this case, but it's not every ordinary differential equation that can solve analytically. And then we have to use it like this. Okay, example. But we also see that the Rk method we have, it actually fares really well with actually a bit lower error. And if you want an even lower error in your estimates, I'm going to share you some options you can give to this OD45. But at least try to Rk yourselves. Solve problems like this. Questions to this? Should I try the other function as well? See how that fares? So dance. Midpoint Method Rk4. Again, we can try to assume error. Like we have bit higher error and actually escalating, whereas this OD45 is self-regulating and fixes the problem for us. But I mean, then again, we have a very long step length in this case. So the built-in OD45 is a lot more computationally extensive. If you were to do this many times, Rk4 could save you minutes, hours. Again, this one, if you want to play with it, is available on the GitHub. And if you want, I can also post it on Slack. Okay. Yes. It's using Rk4 and Rk5. And it's following this idea to use two Rk methods and comparing them. So they compare the result. You don't really know the error unless you have, in our case, the analytical function. So you can only compare the result of both of them. And if the result of both of them are close enough, then it accepts the answer and just continues. But if the answers are too far apart, then it will halve the step length. But it also sees that if they are too close, or if they're too similar, then it can actually increase the step length in order to reduce the computational cost. And next, we will actually learn the trick we're doing in predictor-corrector methods. And of course, the built-in functions in MATLAB, people have spent hours, even days, to perfect them. Just using Rk4 should be straightforward. Yes. We want to reuse function evaluations, func evals. Okay, but next, let us introduce the concept. That is predictor-corrector methods. And actually, in a sense, the points method is a corrected version of Euler's, because Euler is predicting a result, and by doing the integration, you do a correction. But now we'll try to do this in general methods. So we've only worked with single-step methods, but now we'll try to introduce more points. Yeah, for instance, Euler. But now we'll look at multi-steps. So in general, we have yk plus 1 minus 1 yk, and then we had some kind of function evaluations. But now we'll do more of them. Minus 2 yk minus 1 0 yk 1 minus m. H. Then we do the function evaluation. T 1 yk plus 1 plus 1 T k yk and the 0 f of t minus m y 1 minus. Where are all of these? H's and B's are constants that we have to figure out. This is A, I, and B, I are constants. Might have to find. And we need to have some starting values. So when we do the first step, you see that k plus 1 here, but we have a lot of k minus 1 all the way to k plus 1 minus m. We need more than one starting value, or if we only have one starting value, we need some kind of way to start the system. Alpha 0, y1, alpha 1, all the way to y1 minus 1. And then for the break, I'll just let you know this. The M0 have a so-called explicit method. See, if we don't care about this term, we don't like k. But if this Vm is non-zero, is an implicit method. Some implicit methods we can make explicit because we can actually solve for this yk plus 1, put it on the left-hand side, and we can just solve it. And in general, implicit methods are more accurate than explicit ones, but also hard to solve. So we'll do this in the next hour. Questions?